This is a very typical spectrum, and usually I think um, we feel this is more like a hard X-ray, right? Because it has a beautiful exact region, but it's not exclusive to hard X-ray. We can also collect exacts. As I mentioned, if the beamline and the sample are perfect, we can also access the exacts for the temp X-ray. So we have mirrored the sulfur exacts, phosphorus exacts at their APS. They work in the same way as our X-ray, and you can also interpret the data. Right? But I want to, well, we're not talking about exacts this time. We're more talking about the dense part, right? So this the origin region, the dense part. I want you to look at the orange box, and I hope that this kind of picture is firmly embedded in our mind, because that's always the picture that we want to go to when we want to analyze our data. Okay, and that is a very rough, a very simplified approximation of the energy levels in the solids in orange box, right? And so you see, the electrons there, in the ground at the ground state, they actually, they are in their occupied orbitals. Well, actually, they're, we'll go to the complexity of or subtlety of orbitals in future slides. But now let's just say, okay, they're orbitals, or states. Right? So now in the ground state, the electrons are in occupied states. After excitation, that we promoted to their occupied states, right? And that leaves behind a hole. And there are only certain states that is accessible to this electron. When energy is not high enough, the core electron be promoted. It will first go to the occupied states, just above the Fermi level. Okay, but I want you to point out, at this state, the electrons are still bound, which means they still have potential energy. They're still bound by the solids, even though those are occupied states, right? But they're still bound. They're not free to move. So those corresponds to the very initial peaks that you see in the dense part. That's occupied states. And at that state, they still have cancer energy, which is negative. When your incoming X-ray has more energy, then you're able to give the excited electron more energy, and they can push them to the vacuum state. What that means, now the potential is zero. Okay, and what that means, now you're getting very close to generating a free electron. As potential of zero, no longer bounded by the solid, ready to move. So that's sitting on the boundary between things and exacts, right? When your incoming X-ray energy keeps increasing, it is more powerful and is more capable of knocking out the electrons to even higher level. And now it's not just only not bounded, but also gains its own kinetic energy, right? So I think it's pretty much like, our growth paths, right? When elementary school, junior high, is still bounded by parents. College, okay, you have your own freedom, and after graduate school, probably, you start getting your own kinetic energy, especially after earning salaries. So, okay, once they gain kinetic energy, they become the photon electron with kinetic energy. And what they do now, they propagate, right? So, a very fundamental and a very powerful law of physics is duality of the fundamental particles. Fundamental elementary particles, they have a duality, which means they're a particle and a wave, right? So we have now a particle, which is a photon electron. oh, wait a minute, it's also a wave. And what does a wave do? A wave propagates. A wave propagates from the centering absorbing atom, and it will be actually backscattered by the neighboring atoms, right? Because it's a wave. So, this backscattered waves will interfere with outcoming waves of absorbing atom. And what's the result of that? The result is modulation of absorption coefficient in the XAS region. And then we have this kind of oscillation of absorption coefficient in the XAS, right? And a lot of smart people have identified this theory to describe this kind of oscillation. And that is the XAS equation on the basis of which, we fit the XAS, the Fourier transform in XAS, and get extract information about the local environment. Okay, so this is the whole range of our exciting electron, from the call state, gradually first to occupied state, still bound, then to vacuum, and then to put electron propagating and backscattering, modulating coefficient. So that's the whole, the spectrum of the XAS. Okay, so with that picture, I think now we have some understanding of the physics behind the things. So we know that the peaks should have some correlation with all capacities, right? What do we measure? Obviously, we always measure, we want to measure the coefficient, absorption coefficient. That's what we want to measure, right? In an ideal case, where we have the perfect sample and we have the perfect radiation, we can do the transmission mode, right? And that's the most original, most fundamental definition of absorption coefficient that we want to measure how much X-ray is absorbed by the sample. And this kind of absorption, give us a hint or is related to the electronic structure information that we're interested in. But we need to be reminded, this electronic structure of the Zane's part, they have a lot to do with the excited states, right? But think about it. What we really want to know is ground state. So for example, if we talk about titanium 4 plus is 3D0, right? So what we want to do, we want to know is the 3D0 state. But during X-ray absorption, we're creating a lot of 2p, let's say it's the LH. Okay, if it's LH, then we're generating a lot of 2p holes. We're promoting our 2p electron to the 3D. So we have considered a lot of the final state, which is our 2p hole and the 3D one. That's something, carries information in our spectrum. That's something we cannot avoid. And that could potentially complicate our data interpretation. Okay, so I will be covering a lot of theory parts of this, but at the very beginning, I want to point it out, we don't have to be scared away by the theories behind this, because as a spectroscopy technique, a very practical and useful way is to make mirror standards. Right? We don't really have to care that much about the theories, but if we can measure appropriate standards, that is a very convenient way for us to help to understand what's the possible chemical nature of the samples we measure, right? Yeah. So what's happening in the theory and what's happening in the in experiments, sometimes they do not always go hand in hand. And so experimentally, how to get mu? A direct measurement is, as mentioned, a transmission, and that is described by the well-known Beer-Lambert law, right? So when you have transmitting X-ray going passing through your sample, not just X-ray, the same applies to all radiation, infrared, laser, whatever radiation you have, it will attenuate a sample, and attenuation described by the Beer-Lambert law right, which follows this kind of exponential decay relationship between your sample thickness and the signal you get. Right? So you see this kind of exponential decay, and the absorption coefficient is sitting there on the exponent, the mu, right? And also, the x corresponds to the thickness, and also we can get an idea how thickness is so important affecting our experiments. So for example, let's say if we have an appropriate sample thickness that give us the appropriate attenuation, if we double the thickness, then you're not just cutting your, cutting your transmitted X-ray by half. This is actually another, reduced by E, right? So the sample thickness is extremely important for the data quality in the transmission mode. If we have two thick samples, X-ray will not be going through, and we cannot measure any IT, right? And the data will be a disaster, right? And of course, in this two thing, it's not going through. But what happens in some cases, especially when either the X-radiation is not doesn't have high enough energy, as in the case of soft X-ray, right? Or maybe even 10 X-ray, or for example, when we do the in situ experiments, it's not just penetrating the sample; it has to be penetrating the whole system, composed over several whole cell composed of several components. So in those cases, we have to measure different things, and what we measure is the decay products, right? So because we cannot measure the transmission directly, so we have to measure decay products. I think we are educated. There are two types of decay products coming out from the X-ray absorption process. One is electron, the other is photon. And we can refresh our memories about this picture. So once we generate this core hole in our material, because core hole is extremely unstable, right? So the system has to stabilize itself through a shaking down process. And how to do that? It has two choices. One is they're having the valence electron filling the hole, and they release the energy difference in the form of the photon electron. Right. The other is actually in the form of photon. So in the case two, where the photon is released, you see all the electrons there, but a photon is generated and released with the energy that is corresponding to this kind of energy difference during the shakedown process. So there are two types of decay products that we can measure corresponding to the electron yield mode and the fluorescence yield mode. And let's just make fluorescence and photon interchangeable in the next discussions. Okay. I don't know, how many samples you have ever measured for TEY and TFY samples. But if you have a good amount of samples, the chances are sometimes you may find your TFY samples problematic. Right? Especially, for example, if you measure some manganese-rich oxide samples. Let's say you have oxide samples, right? You have cathode samples, and you have a lot of manganese in the system. The chances are you're not able to really get a decent TFY, total fluorescence yield spectrum from manganese. You end up with something like this. Well, this is something I extracted from a literature, and this is measuring on iron, but the manganese has the same idea. So you see, what you measure, what you have is this TFY. You have this kind of dip in your data, right? And obviously, that's not something you can put in the paper. It's not publishable. And there's a reason for this kind of problem. Okay, because when we choose to do the indirect measurements, relying on the decay products, there's actually there's assumption that we already have established. So the assumption is, okay, I'm not measuring the absorption coefficient, but I assume the total amount of the decay products is proportional to the absorption coefficient. So that is saying, if I have more absorbing events, then I'm supposed to get more decay products, right? So that is assumption we have to rely on. And then we can correlate this, decay products to the absorption coefficient, right? Which is the real physical parameter we are after. But this kind of assumption is not always true. It is true most of the time for electron yield. So you probably will not see problematic electron yield data much, but you are very likely to see the problematic fluorescence yield data. So each time you have a fluorescence yield, yeah, I think it's good to be alerted and be aware of some of the potential pitfalls of this kind of measurement. Okay. So this case is showing one example that this kind of a total fluorescence yield is distorted. And why is distorted? There are two problems for total fluorescence yield. Okay, and this requires us to understand the fluorescence process a little bit. So one thing is, let's say, okay, let's say this is to simplify, this is a lithium nickel manganese oxide system, right? And we want to measure the TFY for manganese. So manganese has an LH energy, which is about 650 something. Yeah, I think it should be in the ballpark figure, not very accurate. And so that's the energy of the manganese. Okay. And oxygen has a KH, 1x energy of about 534 something, about 100 EV less. Okay, when we do the manganese, LH manganese, we tune our X-ray energy, starting from 600, right? And let's go over the LH of both L3 and L2. Let's say we go from 600 to 700, right? We go through the whole range and we scan, right? And we also collect the outcoming fluorescence photons. We get a spectrum. The problem is, let's say when we come to the manganese LH, which is about 650 something, we're not only generating photons because of this resonant emission from manganese, we're also generating photons because of non-resonant emission from oxygen. That is something that is very important, for us to understand. Okay, so by resonant we mean the incoming X-ray has the very similar or almost exact same energy as the edge energy, right? So you're resonating because they have the same frequency, they have the same energy. So that's the resonant emission. That means the exciting energy is at the edge. Right? Non-resonant means the exciting energy doesn't have obviously frequency or any difference with the edge energy of absorbent pattern. For example, if we excite material at 650 eV, that is far away from the oxygen KH, which is about 100 eV below. So that is non-resonant. Even though it's non-resonant, it is still generating emission. We're still exciting photons from oxygens. So that is the non-resonant emission. Right? So the total fluorescence actually, the fluorescence actually has both the resonant emission and non-resonant emission. And also, by the way, non-resonant emission is the reason why sometimes we can access a lot of elements, even though the energy, is limited in range, right? So I think Shar has mirrored that at the probably SMR or SIX 5ID. right? So you have access to a lot of elements, right? Even though they're doing the experiments probably at a 7 kV or 6 kV something, right? Yeah, but you have fluorescence access to a lot of elements, including to sulfur, yes. Right. Yeah, sulfur is also included. Yeah. So you do get fluorescence from those elements, even though you are exciting at a very different energy, because those are coming from the non-resonant emissions. Okay. And if you ask the question, why, how do we know that is coming from which element? That is because we have a vortex which can really record the kinetic energy of coming photons. So we know where it is coming from. Okay, but let's get back to the problems. So that is problem number one. Both resonant and non-resonant emission contributes to total fluorescent yield. Problem number two. Let's think about this measurement process. Okay. So we know that the cross section of the volume that is probed is really dependent on absorption coefficient, right? So, for example, if the energy is far below the absorption edge, then it is almost penetrating, right? But when energy comes to the proximity of the absorbing edge, then we have a very large cross section, and also the absorption coefficient is pretty large, right? The result of that is now we have limited volume of the sample. Are we on the same page about this? Right. So what that means is, we are basically probing different sample volumes before the edge, at the edge, and after the edge, right? So now when we are no longer probing the same volume of samples, how can we still use this data? Because your sample volume changes, then you're breaking another assumption that you're always looking at the same sample. Now the sample is different, right? So the count of the outcoming photons will also vary, but not because of there is absorption coefficient thing, but because you are looking at the different sample volumes. We're good? We're good on this? Okay. So those are the two problems that facing the total fluorescence yield, and the solution to that is IPFY that is available at XAS. So I think for people who have measured many samples at XAS, probably have already used this kind of mode, and you already is explained by Adrian in his email. He would give us instructions like which channel corresponds to that, and probably you also realize that you do not always have to use IPFY. But sometimes your TFY is also pretty good, right? You don't really have to debugger, and sometimes your PFY is also pretty good. And but this is I would say this is a bonus for some cases. And it is a must for some cases. What I mean by a must is, when you're not able to really get a reliable TFY or even PFY, then you still, you really have to rely on the IPFY. So let's go back to this example. So you see, the TFY is obviously extremely distorted, not useful at all, right? And then you probably was think about, okay, then how about let's use the ion PFY? So ion PFY is there, and if we compare the ion PFY with the TEY, which is in the bottom figure, you see they have pretty similar shapes, but something different. What is different? Actually, not intensity. If we compare the ion PFY with let's say the TEY or IPFY.
Peak ratio.
Well, yeah, peak ratio is one thing. Yeah, that's true. Yeah. How about the peak width? Right. So we see actually they have a lot, actually an obvious difference in thickness. And yeah, also, yeah, continue right, yeah, there's also the difference in the L3 and L2 ratio, right? So that means they are seemingly correct, but not very accurate. And it is only accurate when you do the IPFY, right? Now it has almost the basically identical feature with the TY. As I mentioned, TY, 99% of the cases you can trust. It will not give you distorted data, right? So TY is something that you can always rely on, is giving you the spectrum you're looking for. But of course, TY cannot probe the bulk, at least to the micrometer size. But with IPFY, you see now you're getting the non-distorted, the faithful variant probing the bulk. So this is a case where IPFY is a must. And I hope we can understand that IPFY a little bit. The full understanding, yeah, really requires, I think it's a gradual process that, we can, gradually digest all this kind of terminologies related to the spectroscopy. But at least we should understand what does I and P stand for, right? I stand for inverse and P stand for partial. So which is inversed? The inverse, what is inverse is actually the non-resonant emission from the oxygen. So that's the essence of IPFY. Okay, so we need a detector that can give us the capability to measure the oxygen non-resonant emission. And we do the re-inverse of that, do the inverse of that. And that gives us this partial of the transition metal that we're interested in. And also I want to mention that this is really a remarkable progress in the spectroscope environment. It's coming from our master thesis of our University of British Columbia student. Not bad. And this is some practical considerations. I think usually each time when we get the data from iOS, Adrian would give us very detailed instructions, how to interpret data, right? Because we usually have several columns, and he would give a very detailed explanation, which column to use and what do they mean. But the idea is, we can understand what they are trying to do is, which is shown in this equation, they collect the data from oxygen PFY, which is non-resonant emission, right, as I mentioned, and that is normalized by the gold mesh current. So, you can take consideration of the possible flux of incoming X-ray, and that's basically a probability. And you do the inverse of that. That gives you IPFY transit metal, and that's what you get. Okay, so you don't have to worry about the equation details because each time, as I said, Adrian will always tell us very clearly what we should be doing, but you get an idea what is really what is really meant in this kind of equation. So it's inverse of oxygen non-resonance. Okay. And usually this is required when we do some transition metal that's so close to oxygen, for example, like manganese, iron, and probably chrome. Okay. It's not so much concern if we go up in energy, let's say we move to nickel. So you already do not have any concerns about nickel. The reason is nickel has a much higher energy. Nickel LH has much higher energy than oxygen KH, right? So you are really generating a very small amount of oxygen non-resonant emission. And that is not much of a concern. And that is also true for copper. More notes on electron yield and fluorescence yield. So I think this paper is also very important for us to understand our data. So this is describing the probability of the decay channels for different elements. Right? As I mentioned, when we introduce a core hole in absorbing atom, what follows is a decay process. Then we need to fill up this hole and shake up the whole system, releasing the energy either in the form of electron or in the form of photon, right? But the important thing is they do not have equal probability. The probability of yielding a photon and the probability of yielding an electron, they can differ significantly. And so you see in the yellow region, origin electron yield is the dominating process of decay. So that is saying, when we're looking at elements like carbon, oxygen, nitrogen, fluorine, etc., 99% of the decay process is through the origin electron. Only less than 1% really give us the fluorescence decay. So what does that mean? That means, okay, measuring fluorescence is, has more challenging, could be more challenging than measuring the electron yield, because you have so many electron yield decay process going on, right? But this kind of proportion changes, and you see we have this kind of crossover at around atomic number about 33 something. And if we look at the regions of our interest to the transition metal, which is about 20, between 20 and 30, you see now they have a, roughly comparable probability between fluorescence and electron, right? So I think that's something we need to keep in mind. Yeah. Also, actually, so I want to also mention the discussion I had with Sharp the other day about their, their trying to link the fluorescence intensity with abundance of elements, right? So, so in those, what I mean is, in general, sometimes we feel, okay, if the fluorescence signal is high, then it means the abundance of this element should be high, right? But that kind of comparison should be, be made only upon their, close atoms in the periodic table, right? So, for example, I cannot make comparison between oxygen and the nickel. They're too far apart. They have totally different probability of fluorescence, right? So, so that, that makes comparison not doesn't really have any sense. Another thing I want to mention is when we measure the TUI, in fact, the majority of the signal really comes from the secondary electrons. So what is secondary electron? Secondary electron is secondary. It's not something primary, right? So origin electron, for example, is the primary because it's directly coming from the decay process. And secondary electron is something coming from the cascade of origin electrons. So let's think about the process. When we have a lot of origin electron decay happening, right? So those origin electron decay will try to escape the solids. During this path of escape, it will interact with the neighboring solid materials. Right? And that's a strong interaction. That gives rise to another decay process. So this kind of interaction. And those are the secondary electrons. And those secondary electrons already have a pretty low kinetic energy, and they make up the majority of the electron yield that we measure. Okay, so it's made up of the majority of the secondary electrons. But you see, this still has a lot of origin with the generation of origin electron, right? Because it is origin electron that kind of generated this kind of secondary electrons. So yeah, they still have a lot of relationship. Another thing is we need to be aware of the different interaction mechanisms between photon and electron, right? So for photon, it's weak interaction, right? So photon, when photon is transmitting through a meteor, it's basically follows the Beer-Hammer law, and it usually can, the beam path can be around micrometers. But if it's electron interacting with matter, then that is very strong interaction. Electrons have a very strong interaction with matter. The consequence of that, they have a very low, their inelastic mean free path rate. they're not really able to escape the solids. The solids have a certain thickness, and that is why whenever we have a technique that has electron embedded in the main, it is very likely a surface technique, right? Because the electrons cannot get out. And the examples include the electron yield of the XAS and also the XPS, the X-ray photon electron spectroscopy, which is utilizing photon electrons. Whenever you use electron, whether it's the electron or photon electron, they have strong interaction with solids. They have a very small escaping paths. They probe the surface, very surface of this. Okay, so those are very two big differences that we want to pay attention to. Okay, then how do we understand the data? So we collect data, we get a bunch of peaks, and a conventional way is to label the peaks, right? We check the literature and see what they call it. They may call this this a T2G peak, EG peak, whatever, and yeah, that's a common practice. But when we go back to the fundamentals, I think we need to really understand what is really going on here. Okay, as I mentioned, this absorption process really involves two states. One is the ground state, right? The original electronic structure our material had. The other is excited states, which contains both a warm core hole and also an additional electron in the valence. Actually, in the LUMO area, right? In the LUMO. So this kind of excited states is always embedded in the spectrum of our data. Okay, I think this sentence has to be emphasized many times before we really appreciate how important, how fundamental, how prevalent it is. Our XAS spectrum always has information about the final state, which contains the core hole. Okay, because I think usually when before we come to this sentence, when we look at the data, we probably do not really think about that much, right? We do not really think about why so bother about excited states. Okay, we need to consider this because this really relates to our interpretation of the data. So depending on the nature of the hole and valence, sometimes we can just pretend it's not there. Sometimes we can do that. Okay, sometimes we just can regard the XAS valence part at approximation of the LUMO, of the unoccupied states, but of course with the correct symmetry, right? Because the spectroscopy always involves the selection role, so it has to be symmetry projected. But in some cases, we just cannot do that. We see the peaks, but this peaks has nothing to do the real unoccupied states, what we have, because they are complicated by the presence of core hole. That's the message I wanted to give. So what is simple and what is not? For traditional oxides, the typical cathode we started, KH usually is a simple case that we usually just look at the peak and make some labeling saying, okay, this is T2G and EG. Probably 60% of people will not say you're wrong. And it's roughly correct. Yeah, we do this kind of make correlations. That is because the final state is the warm hole in the 1s and the excited electron in the 3D. Because 1s and the 3D, they have extremely different energy levels. They don't speak to each other. They don't interact with they don't interact with each other. They don't correlate with each other. They're 99% of the time they can be treated fully independent. They have nothing to do with each other, right? So in that case, this kind of a core hole and valence electron correlation is little. It has a very limited influence. And in those cases, we roughly can treat the data as this kind of a one electron picture. So what we mean by one electron picture, that means is, we can just think about, this kind of orbitals or states, then we can put one electron there. It's not really changing anything. We can directly make a correlation between the length peaks and occupied states. What is complicated is the L edges. Because now the core hole in the final state, the core hole is on 2p. And excited electron is on the 3D. And this 2p and 3, they have pretty close energy level, right? Yeah, I think this is easy to configure because think about the covalency of transition metal oxides. Why transition metal oxides usually they are not ionic? Because there's a strong covalency between transition metal 3D and oxygen 2p. Why that? Because they have close energy levels. Okay, so in that case, the correlation between the hole and the valence is significant. And there's no chance to really, still pretend it's one electron. It's many electron power. Okay. Okay, and yeah, this could be a little bit complicated, and I guess we don't really have to understand every detail of that at one time. We can do it repeatedly through many iterations. But the main idea is I hope you get an impression. I hope some of the key points, can be embedded in your mind. So you start to appreciate some of the key points. The key point one is many electron wave functions is fully different from the single electron wave function. So what is a single electron wave function? We have been used to talking about orbitals, right? We talk about orbitals all the time. Okay, let's say this is a 2p, this is the 3D. Okay, this is the 3D xy, this is 3D this square minus r square, whatever. Those actually, they are all single electron wave functions. They are all the analytic solutions to the hydrogen-like Schrodinger equation, right? So when you have a Schrodinger equation, and in your Hamiltonian term, if you do not have electron interaction, you only have the kinetic energy and the potential energy. It's totally solvable. You can exactly solve the Schrodinger equation with a single electron. And then you get exact wave function of those single electrons. Right? And that's what you get the orbitals. You basically solve the Schrodinger equation, single one electron Schrodinger equation, you get a bunch of solutions, and we can label them using quantum numbers, then we get orbitals. Right? We have their main quantum number, the orbital angular momentum, yes, yeah, azimuths, and also the azimuths, the magnetic momentum, and also the magnetic, the spin, when you label all of them, you get that's basically a wave function, right? You just label wave functions. But this is an extremely simplified way, because in many electron systems, let's say we don't have to go to very complicated. I'll give an example about helium. Helium probably is the most simplest case where we have two electrons, right? Even for something like a helium, we only have two electrons. There is no way to solve the Schrodinger equation analytically, which means you cannot get an exact solution because electron interaction term, right? The only possible way, and that's what people have been trying, is approximation. If we cannot get exact solution, how about let's do the approximation? And as a matter of fact, all the calculations we rely on, no matter whether it's molecular optical theory or it's a DFT calculation, it's all based on the approximation. we have to approximate in a certain way, to get the solution that is as close as possible to the exact solution, right? So I hope now we start to appreciate this problem with our many electron wave function. Those kind of orbitals, which is the solution of the single electron system, sometimes is not applicable to describe the many electron wave function. One of the reasons is, in order, when we make approximations and we can construct their, different bases, right? So we can make linear combinations. Let's say, okay, let's assume this ultimate wave function is a linear combination of certain orbitals, which is a certain single electron wave functions, certain orbitals. But ultimately, they still have to obey the physics law. And the physics law are 3 laws they have to obey. That's the minimum requirement for them to be a possible legitimate wave function for many electron systems. So those 3 laws are the pillars, they are the minimum requirement. So one thing is electron is a fermion. What that means is it is asymmetric with regard to interchange of electrons. Okay, if you find the language too abstract, bear with me. I think, let's just go through them one by one, so we can have a memory. Okay, let's just have a memory. Let's just have some impression first. First of all, electron has to be fermions. That means when you have a wave function, many electron wave function, this wave function needs to be asymmetric, which means it should change the sign if you interchange the position of 2 electrons. Okay, that's minimum requirement 1. Number 2, it has to follow the Pauli exclusion. I think we know the Pauli exclusion, right? So you should have a unique set of the 4 quantum numbers, right? You cannot have their, same set of quantum numbers, because it's exclusive. You must have a different address for each single electron. The third one is indistinguishability. Okay, what that means is, when you do the interchange of electrons, your property should not change. Or to be more specific, your electron density should not be changed. Because electrons, they are all identical. If you change the identity of 2 electrons, you doesn't change the electron density of the whole system. Okay, before we are completely bewildered by those kind of abstract concepts, let's move on, okay? So I'm going to give you a very simple example of the helium, and the start appreciation of the, what the many electron wave function should look like, and how that is different from the typical orbital picture we have, and how that is, very powerful in making spectroscopic predictions. Okay, that's the goal I want to have in here, and I'm trying to, use the helium 2 electron as an example. So many wave electron functions, it actually just like the single electron wave function. It has both the spatial part and the spin part. Okay, so please be reminded. In a lot of cases, probably where we're used to this kind of spin up and spin down, right? Probably +1 half and -1 half. That's not the function described spin. The spin also has to be, probably described by a function. Okay, and the function is a spin function that is part of the total wave function. The total electron wave function, so it contains both the spatial part, that's relating to their, in terms of orbitals, that's relating to their, orbital shape, right? How big they are, how localized they are, what kind of shape they have, and the spin part is also a function. Okay, so let's accept this. And this is an example of excited helium atom, probably the most simple the excited system we can ever have, right? So the left column is optical filling picture. I think, we have been very used to optical filling. Okay, now we have a 1s, 2s, we have two electrons. How to fill them? Okay, we probably have both on spin up, both spin down, one spin up, one spin down, right? You change the sequence. We have these 4 cases, right? That should be very easy to understand, thinking about the optical filling picture. So what I'm trying to tell you now is this picture is simple but wrong. Even though it's very common use, right? It's wrong. It's not useful, in the spectroscopy understanding. To understand the spectroscopy, there's no way around but to really have appreciation of many electron wave functions. And the many wave electron wave function is on the right. Okay, and this is something I directly copy-pasted from the MIT Open Courseware 5.61, that's a physical chemistry course. And so they already have a very nice duration and the results. I simply just copy. So these are the wave functions describing the excited two electron system. So one thing is you probably see how complicated they are, right? But now you see, okay, that they have both the space part and the spin part, right? And also for the spin part, you see the kind of alpha, beta, and that corresponds to different spin state. Either the spin up or spin down, right? Alpha corresponds to spin up and beta corresponds to spin down. And then you have this psi 1s, psi 2s. That's orbital. That's the fundamental orbital or the one electron wave function that we can use to construct these many wave functions. Okay, so and the R1, R2, they correspond to different elements. Okay, so for example, if you have a psi 1s R1, that means we put electron 1 in 1s and electron 2 in 2s. Okay, we're on the same page on this, right? Okay, so you see that's the legitimate wave functions for this 2 electron system. By legitimate, what I mean is they satisfy the 3 fundamental principles of quantum mechanics. One is electron should be fermion. So if you check all these wave functions, they are asymmetric upon the exchange of R1 and R2. That's very easy to check. You can check, it's asymmetric. So it satisfies the requirement of a fermion, and it satisfies the Pauli exclusion principle. R1 and R2, they're never in the same state, right? They have different wave functions for different spin, right? Okay. Number 2, Pauli exclusion principle, check. And number 3, they are indistinguishable. So if you change R1 and R2 in any of wave functions, you will not change the probability of this wave function. Right? Probability of the wave of the electron, that is the property, right? That's the property we're talking about. Also, that's the electron density. Okay, so this is set of wave functions. They're legitimate. They can satisfy all those requirements. And what is important is now we see there's actually no one-on-one correspondence between the orbital filling picture and the many electron wave function. Right? So, for example, if we look at the first picture of the optical filling, so we have both 1s and 2s spin up, right? So you cannot really find any wave function corresponds to this. There's no correspondence. What actually you'll find is, you'll see that this kind of wave functions, they are more like the linear combination of the states on the left, right? Okay, before I get this too complicated, I just want to proclaim this message again. There is no one-to-one correspondence between the orbital filling picture and the legitimate wave function. And you'll see very shortly, optical filling picture cannot predict anything from what we measure in the spectroscope. But there's this kind of many electron wave function they can. Okay. Why they can? Because if we look at wave functions of the helium, so you see if we can calculate the energy of all those wave functions, right? That is done by plugging the Schrodinger the Hamiltonian, because it has Hamiltonian, the quantum mechanics. So you plug in the wave function and also the Hamiltonian operator, and you do the integration, you get the energy. That's how you calculate the energy. If you calculate energy for all these four wave functions, we will find that all these three red boxes, they have the exact same energy. They have different wave functions, they have the same energy. And they correspond to a triplet. And the second wave function in the blue, it has its own energy, and that is a singlet. And this singlet and the triplet is something that people can measure in the spectroscopy. Because when people measure the excited helium, they will indeed find a triplet and a singlet, two lines corresponding to the excited state of helium, right? And again, we'll never be able to tell triplet and singlet if we think about the optical filling. So if we look at optical filling, what do we get? We probably feel, okay, there seems to be two kind of states, right? One with all the paired up and also paired down. The other, one is they have the same spin, the other with a different spin. That's probably the conclusion we get. Okay, so I hope this can give us the some feeling about the what is really why many electron wave function is important. Okay, yeah, like I said, the take-home message is the peaks, they do not always correspond to orbitals and bonds. Sometimes they do, right? For example, as I mentioned in the key edge, yeah, they have a rough correspondence, but it's totally not the case for transition L. Okay, and yeah, that's the message I want to get. Okay. Before I move on, any questions? No questions? Okay. Or do you want to go on? Okay, pretty silent. Okay. Let's see. Yeah, actually, we talked about this before. Yeah, I was going to go through with term symbols, but I'm not sure if we really should keep continuing. Okay, maybe I can summarize what I have lectured so far. So to understand the XAS process, right, we need to understand the electronic structure of our materials. So we have different levels, and but we need to appreciate, strictly speaking, the physics of XAS involves excited states. Okay, so I think you can't forget anything what I have been saying, but I hope this message goes to your heart that the XAS is embedded with the final state, which has a core hole there. Okay, this core hole sometimes is making your interpretation complicated, sometimes not. Okay, so when it's not, I think, we can roughly establish correspondence between the peaks and maybe some bonds. Bonds, in essence, is actually also opposite. So that's what we can, and also practically a very useful way is to mirror standards. Practically, that help us to interpret the data a lot. But the complicated side is when the presence of this cohort cannot be ignored. Right? And that's the case for transition methodology. And understanding of that requires us to really to go to the manual electron wave function, which is probably not easy concept to understand. But that's the correct way to understand it. Right? Yeah. So yeah, I guess that's the main message I want you to do.